Greetings everybody, and welcome to our first example of using dot products. So what we're asked to do in this particular problem is that we're given a couple of vectors u and v, and we're asked to find the component form of the vector w, which is going to be the projection of u onto v. So let's take a look and see exactly what this problem is really asking. So suppose we're given two vectors. We're given one vector that's going to be u, and we're given another vector that's going to be v. We can then kind of ask ourselves the question of how much of the vector v is in the direction of u. And for that, we're really kind of asking the question that if I kind of look at maybe another vector, where if I draw a line that's going to be perpendicular to the vector u, that if I look at another vector, I can say, well, how much of v is really going to be in that direction? So that if I were tracing this out, I would have another vector that's kind of equal to that length in the same direction as u. So kind of what I'm thinking in this case is, what is that vector? That vector is called the projection of v onto u. Now, the notation for that is really given exactly by the problem, in that if we look at the proj, really meaning projection, and then the subscript u is there to tell you onto what vector you are actually projecting, and then we can think of this as really a function that takes in a vector and it's going to return us a vector. And the vector that is taking as its input is the vector v. So now the question is, how do we actually compute this new projection of v onto u? So how we go about answering that question really just kind of comes down to our familiar right triangles from trigonometry. That if we happen to know that the angle between the vector u and the vector v is going to be theta, then at least the magnitude of this new vector, the magnitude of our projection, is really just going to be given by, if we look at the cosine of theta, that's going to be the magnitude of the projection being the adjacent side divided by the magnitude of our vector v. And so if we kind of rearrange this just a little bit, that we get the magnitude of the projection is going to be equal to our length of v times the cosine of the angle between u and v. Well, if we stop to think about, we know what the cosine of that angle, or we've seen an expression that really involves that. And that's kind of coming back to our dot product. Remember that our dot product of u dot v is actually going to be equal to the length of u times the length of v times the cosine of the angle between them. And so if we kind of rearrange that expression a little bit, what we have is u dot v divided by the length of u is going to be equal to the length of v times the cosine of the angle theta. And that in turn is going to be equal to the magnitude of the projection. So we're kind of getting an idea of how we can, or at least how long that vector is going to actually be. So the idea then is So kind of our last idea is to do this, or a strategy. We scale the vector u to become a unit vector, then use the magnitude above to obtain the projection. Because after all, the projection vector is going to be a vector that's in the same direction as u, because that was our original question. We wanted our projection, how much of v is in the direction of u. So we're really just kind of taking our taking our vector u, turning it into a unit vector, and then scaling it back up to the magnitude that we're actually going to need for our projection. So let's kind of put this together and see if we can obtain a real formula for what the projection of v onto u is actually going to look like. So for our vector u, if we wanted to turn that into a unit vector, so remember how we did that we scale it by the reciprocal of its norm. So if we take the vector u and normalize it by its length, then we obtain what is going to be the unit vector in the direction of u. So now what we then needed for the projection, so our projection onto u of v is going to just be this unit vector, so 1 over the length of u times u, and now we want to scale it up by our desired length. And kind of coming from our dot product, we know how big that was supposed to be. That's actually going to be u dot v divided by the length of u. And so what we end up with is an expression of the form u dot v divided by the length of u squared times u. Well, to kind of bring this back home again with the dot product, our length of a vector squared can really just be written as the dot product of the vector with itself. So we really have u dot v over u dot u, and then that is scaling our vector u. And so we obtain a formula for actually computing the projection of v onto u in any particular case. So we can do that really just in terms of dot products. So now we're able to actually take that value, take those two vectors, and we can scale them appropriately to obtain our projection vector. So then in computing the projection, what we have will be our u dot v divided by u dot u times our vector u. So our u dot v is just going to be our 4, negative 3, dotted with our 3, 3. And so that's going to give us a 4 times 3 is 12, minus 3 times 3 is 9, so we have a value of 3. For our u dot u, we have our 4, negative 3, dotted with 4, negative 3, which gives us 16 plus 9, or 25. And so we have a scalar of 3/25 times our vector u, which was for -3. And so this is going to then give us a vector 4 times 3 is 12 over 25, and -9 over 25. So here we've obtained our vector projection. I hope you've enjoyed this video, and I will see you guys in the next problem. Take care.